We talked last time about the real numbers. We started but didn't finish a proof of, okay, so we had this whole conversation, Simplicio and Socrates went back and forth. Here is the theorem that I want to discuss. But let's just do it in natural language. I'm going to let this load. Actually, I'm just going to slide this all the way over. And then let's talk in natural language. Okay. Well, yeah, let me state the theorem and then let's talk about it. So here's the theorem. We saw last time, the reason Cauchy sequences from the naturals to the rationals converge. They do not converge in the rationals, but they converge in the reals is that John?
I think it was like we defined the reals to be
They are the reals. Exactly right. Exactly right. They are the reals. They are the reals. Okay, so the reason Cauchy sequences in the rationals converge to real numbers is because real numbers are Cauchy sequences in the rationals. It's almost by definition. What about Cauchy sequences in the reals? What about Cauchy sequences in the reals? Do they converge? Maybe we need, now that we have limits in rationals, we've added a whole bunch more things. Maybe we need a whole bunch more things that we have to do in order to have Cauchy sequences in the real numbers converge to real numbers. What else do we need to add to do so that Cauchy sequences in the reals converge? We need to add some kind of hyperreals, surreal numbers. What do we need to add on so that Cauchy sequences of real numbers converge? Nothing. Nothing. We need to add nothing else. Nothing. Okay? So here's the theorem. Cauchy sequences in R converge to real numbers. Converged. A Cauchy sequence in R converges to some limit L in R. Okay? Here is your, let me give you one little theorem. So there's a theorem called real, or definition really. There's a definition called real of Cauchy. Okay, here's a new definition, real of Cauchy. If I give you a sequence A from the naturals to the reals, and it's actually convenient not to have to give you A explicitly, but rather A will be inferred from the information. The information is Cauchy. So HA is the fact that is Cauchy. I'm sorry. The whole point is that we're not going to the reals. We're going to the rationals. So if I give you a sequence of rational numbers satisfying is Cauchy A, you give me a real number. Okay? I won't discuss how this is proved. And we have a theorem. We'll have a theorem. What did I call this theorem? Let's make up a name. Seek lim of Cauchy or something. Seek lim. What did I call it? Did I call it seek lim of Cauchy? Let's see. Scroll down. I guess scroll up. Seek lim. Did I forget to say what I'm calling this? New theorem. Seq-lim of real. Oh, really? I gave it a horrible name? I guess I gave it a horrible name. Okay. Seq-lim of real of cow. That's what I called it. Seq-lim of real of Cauchy sequence. What this says, this theorem says, you give me a sequence, which will be inferred, hence the curly brackets. You give me the fact that the sequence is Cauchy. I'll give you a proof that seq-lim, remember what seq-lim is, for all epsilon there exists an n, yada yada. The sequence is A, but now I need A that goes not from naturals to rationals, but naturals to reals. So it's really a function that maps n to A of n as a real number coerced into the reals. Okay, A starts out being a rational sequence. I want to turn A into a real sequence, so that's just the function that maps the natural number to the value of A of n, but now instead of a rational number, instead of 3/2, it's the infinite sequence, 3/2, 3/2, 3/2, 3/2. Because the way seq-lim works is I can only say something has a limit if the limit is of the same kind. And I'm about to put a real number here. What do you think is the limit of the sequence A? Given that it's Cauchy. I've lost everyone. Real of Cauchy gives you a real number. What do you think that real number is supposed to be? The limit.
Yeah.
Okay, so that's what I want to put here. I want to say the sequence that maps n to an, but bumped up to a real value is the limit that I claim, that I define back here. Okay, and so how do I say that? It's real, let me put it over here. Real of Cauchy. And now I don't have to write A, it'll infer what A is from HA. Okay, and then this has a proof. So there's a way to do it, and I do it in the I'll just show you. So there's another theorem. I want to move past this stuff. I do want you to know what the real numbers are, but I want to go back to, let's take the red pill again and go back to the real numbers being the real numbers. Let lean do all that under the hood. I want to get the actual calculus sequences. We've done sequences. I want to get the series, integrals, derivatives, the fundamental theorem, all that good stuff. So we're not going to belabor this point beyond today, which should have been last time, but whatever. There's a theorem that's in the library that if you have a sequence of rational numbers that's Cauchy, then it converges. By the way, this A dot is the fancy way of doing it's the fancy way of upgrading a function from the rationals to the reals. It'll take care of that automatically. Then we have a definition. Why is it non-computable? Okay, let me not go into non-computable. It's because it's defining a real number, and real numbers are infinite sequences or equivalence classes of infinite sequences. Roger. Yes, I'm sorry. Thank you. Thank you for alerting me to that. Okay, so given that a Cauchy sequence in the rationals does converge, choose that limit and return that limit. And then given that we got it from the fact that it converges, here's the seq-lim of real of cow. If I have the Cauchy sequence, then the theorem says seq-lim of A is this value L. And the reason is that's what the choose specification proves. Okay, I don't want to even look at this code. So forget that this code, forget that you saw this code. Let me put this back over here. Here's my question for you. How do we actually, okay, so given a rational Cauchy sequence, we know how to say what its limit is supposed to be. That's this real of Cauchy. And we have a theorem that says that that real of Kausik of that sequence is the limit. In other words, seq lim of the sequence, but now bootstrapped up to the reals, has that limit. Okay. Given those two things, how can we formally, so let me slide this over here. This will be our quiz. How do we formally state the fact that a Cauchy sequence in the reals converges in the reals? Okay, let's try this. So, quiz, how to formally state that Cauchy sequence, not prove, but just state in R converges to R. And let me zoom out so you can see these two names of theorems in case you find them useful. Keeping in mind that the way we actually construct real numbers is as Cauchy sequences of rations. What could this possibly mean? So let me start you off. So let's do some scratch work. I want a sequence x0, xn, and so on in the reals. But what are real numbers? X0 is really, or at least has a representation. I'll put a bracket since it's equivalence classes, but I don't care about that right now. It's really what? Yeah, let's write this as Q00, Q01, Q02, and so on, where this is Cauchy sequence in the rationals. So what is a sequence? And now what is X1? Topic. Right. Q10, Q11, Q12, and so on. Okay. So this ensemble, so the ensemble of X's, what is its type? It's a matrix. How can I write that? It's a sequence of sequences. It's a sequence of sequences. So it's a map from the naturals, meaning the natural is the index, to the naturals to Q. It's a matrix. Okay, this is the I component. This is like going down I. That's what the first guy is. And then how far over do you want to go? That's the second component, J. And this will give us a Qij. Maybe we should call this Q. So X is really, the sequence of Xn is really a matrix of Qs. Okay. Each Xi is itself a Cauchy sequence. So what hypothesis do we want to give to the Qs?
Is Cauchy,
Yes. Q of I, exactly. Q of, let's say, n. Q of n is a sequence. Q of n is like xn, is like this, the nth sequence. And so for all n, the rows are Cauchy. That just means that we have a sequence of real numbers. Does that make sense? And now, how could we say that that entire ensemble is itself Cauchy? So let's have a hypothesis on X. What is Cauchy? For all epsilon, there exists an N right. Something minus something is less than epsilon. What are these two real numbers? They're sequences, but we have a way of converting sequences. You're right, they're sequences. We have a way of converting sequences to their limits. Right. Exactly. Real of cow seek. And then I have to give a proof that something is Cauchy. Jeffrey already said HQN or M, I guess M. It doesn't matter, but to be consistent with what we had before. Let me try to write this in English. Minus, so that's the limit. So we have this sequence. And so being Cauchy says for all epsilon, there's a capital N. Let me try to draw this matrix here. Here's Q00, Q01, Q02, yada, yada. That converges to, I'm going to just write X0, but X0 really means real of Cauchy or whatever. Cow seek, I guess. Cow seek. And then, HQ of 0. And then we have Q0, 1, 0, and Q11 and Q12, and that converges to this thing. So what's going to go here? Brandon.
Well, a real cow seek HQ.
Exactly. Cow seek HQ of N. Okay, that's our second hypothesis. So our first hypothesis is when we go horizontally across, these are all Cauchy sequences. So each xi is represented, here's xn, it's represented by a Cauchy sequence of rational numbers. And the second, that was HQ. HQ says when we go across, we get something that's Cauchy. HX says these limits are also Cauchy. Okay, so these are our assumptions. And what is our goal? We want to find a limit here. Let's call this limit L. Brandon.
Is this where we use like the Alexi for
Almost, not quite, but how are we going to express L? What does it mean to give a real number, Savik?
I forget what that thing is called, but like there exists such that like whatever like our helper function is to get like the real from the sequence, and like we plug in this sequence and it should be like some element.
Yes. So let's say, so to say L, remember L is a real number, but real numbers are actually Cauchy sequences of rationals. So we actually want to say that there exists a Cauchy sequence of rationals. Let's call this, I don't know, Y, Y0, Y1, and so on. So there exists a sequence Y from the naturals to the rationals with two properties. What are the two properties? Akil? They'd better be Cauchy, so it converges so that there is a real number, right? So is Cauchy Y, And what else? Yes, and the limit of the xn's should be the real number that you get in the limit of the y's. Okay, watch how this is written. Oh, in fact, you can see it here. I don't have to well, maybe I'll reload the editor just so it doesn't have all that red there. Zoom in. Come on. Okay. So here, what happened? So let's just look at our goal. Our objects are Q, which is a matrix, and N. Our assumption, HQ, is that along every row, the Q's are Cauchy, and that the limiting values are also themselves Cauchy. So along each individual column, once you go out to infinity, is Cauchy. So this says for every epsilon, there's an n, so that for all n at least n, and for all m at least n. Unfortunately, it tries to hide, when it has a really complicated formula, it tries to hide what's going on. But if I hover over this, I think it'll give us HQM. And then here it's HQ of n, exactly as we said, that's less than epsilon. And our goal is to show that there exists a y. There exists a proof that that y is Cauchy. So the way to say this is to say there exists not only a y, there also exists, and I need to be able to reference this later. So I'll say there exists a proof that y is Cauchy, hy, such that the function that maps n to these limiting values, these xn's, converges to the limit of the y's, and I need to know that the y's are Cauchy in order to be able to say that they have a limit. Okay, does that make sense? So I'll write it here. So we have to have a Cauchy sequence, first of all. Before we can prove that it's Cauchy, we need the sequence y. We need to show that the sequence is Cauchy. And once we've shown that the sequence is Cauchy, that means it has a real number limit. And what we want to say is seek lim, the function that maps n to the xi's, but the xi's are real of Cauchy sequence applied to HQN. That's the sequence of xn's. And what is its limit? Exactly. Real of Cauchy. I would say y. But it doesn't take y as a variable. What does it take as a variable? Y is an implicit variable to figure out what y is. Hy. It needs the proof that y is Cauchy. So it actually takes hy. Well, you can see it right there. Does it make sense that this is the statement of the completion of the real numbers with respect to, yeah.
What's the first argument? Like, what is
Seek lim? Oh, seek lim. Let me just remind you, seek lim. Can I hover over seek lim?
No, I know what sequence does. But
Oh,
I like in this example.
yes.
Where we actually.
We're plugging in the xn's. We're saying the sequence of the real numbers that you get out of the xn's is the real number that you get out of the y's. This thing is L, this thing is L, each of these is an xn. Does that make sense? Okay. Hand the quizzes over to Joe, if you don't mind. Maybe we should have yeah, too late. I was gonna say we should have a better problem for the quiz than how would you state it, and we went over the statement. Okay. How do you prove this statement? Where are you supposed to get this sequence? That's too hard for a quiz. It's probably too hard for a test. Where are you supposed to get this sequence? Yeah.
I don't know, the only thought that's coming to my head is it's some kind of like limiting sequence, so it's like maybe like go down on each column or something.
We certainly have to use every column, and we certainly, like, what we want to know is go far enough in that when you go far enough down, that you get a sequence that somehow is going to L. You have to somehow make use of the whole matrix, but how do we go deep enough in the matrix? This is the blue pill again. Jeffrey?
Can you go in the diagonal?
Excellent suggestion. Stop it. What were you gonna say?
I'm gonna suggest that, but I was gonna say, yes, some epsilon, and then you get like an n for each row, you just add all the like super. Are like sufficient or
Let's come back to your point. Let's try the diagonal. The diagonal is the very standard argument that says, if you have a large matrix and you want to go down and over, just do it along the diagonal, right? Do it along the diagonal. So let's try attempt, maybe I'm giving away what's going to happen, but attempt 1 is try the diagonal. In other words, yi will be, or the ith term is qii. Yeah, exactly. Y0 is q00. Yeah, qii. Exactly right. Okay. So why is this sequence Cauchy? Let's see if the sequence yi is Cauchy. So what do we need to know? Is this Cauchy? And then does it converge where, you know, does that, if it's Cauchy, then does it converge? So we need to know for all epsilon, does there exist an n, so that for all n at least n, and for all m at least little n, yn, so this is qnn minus qmm, or maybe the other way around, probably the other way around, is less than epsilon. Is this true? And if so, why is it true? How would we make progress towards proving something like this? So where are we geometrically? We have some qnn over here, and we want to get to some qmm over there. And we want this distance to be small. I mean, not the physical distance in the matrix. I mean, the distance between these two real numbers. Sean?
You would want to go right and then down.
Yes. We would want to go right, and then we would want to go down. That's the idea. In fact, maybe we want to go all the way over to the right, and maybe we want to go all the way over to this limit. This guy's got a limit, that guy's got a limit, because we know that the limit of the sequence qni has a limit which is xn, and this has a limit which is xm. So maybe we want to go all the way over here. These two differ by a small amount because they're Cauchy. That's this hx assumption. And so we'll be in good shape. What goes wrong? John?
Something like when we go all the way to the right, you kind of like locked into, you kind of like fix the x's, so you can't really control the distance between x's.
Well, so we're trying to show, let's remember what we're trying to show. We're trying to show, for all, given an epsilon, we want to know that when we go far enough down in the matrix, far enough down in the rows, if you get to the nth row and the nth column, that will be close to the mth row and the mth column once you've cut off the first few rows and columns. Right? So we're sort of already in this part of the matrix. Roger, what's the problem?
I tried this problem.
Sure.
So like, it's like Q00 is zero. Like,
Y0? Y0 is Q00, the first term?
it's just a base.
Sure.
And then like the rows mean like, you put a number in the digit after the decimal point. Like for Q01, it's one, so like you put like a one in the, like it's 0.1.
Doing like function fiction.
Yeah, like the cancer, like a little bit.
Well, they can't, okay, yeah, go on, finish your thought. I'm gonna try to understand it and see what I can write down.
Wait.
Yeah. Here.
Oh.
Like,
Oh.
I think you're drawing on the side, draw on the white.
Okay.
But what are these numbers? I don't understand.
Oh, like it's the Q's.
It's the what?
It's like no, it's the Q00 Q1.
So what is Y1? Y0, I need to be given a sequence of rational numbers.
They should all converge to zero.
Y to 0.
No, like it's like what I'm trying to construct.
Okay, okay.
Um,
So what's Y of 1? The first one you're saying start with Q00.
yeah,
Fine.
yeah. Um,
What's Y of 1?
it's still the diagonal.
Oh, it's still there. So Y of 1 is QY11.
Yeah, I think we
And
can,
Y of 2 is Q22.
I think we can do that.
Okay, let me explain why we can't,
Oh,
which is why it was attempt 1.
oh.
Yeah. It's very tempting to do the diagonal. The diagonal is what these kinds of arguments are supposed to be doing. Sabi, you want to say something?
Where do you go, like, on this proof? I just wanna make sure I understand geometrically what we're talking about.
Yes.
You're saying that if you go far enough and like pick some initial top left corner of like a submatrix, and like just everything down there, you pick any two elements, it'll be within ourselves.
Well, I don't know that that's true.
But we're trying to prove that is true.
We're trying to prove something like that. We're trying to prove, I mean, if you look at this goal, what this goal says is when you take these sequences and you take each of them out to infinity so you get a real number, then you somehow have to construct a sequence of rational numbers out of this matrix of rational numbers. That sequence we have to prove is Cauchy. It's going to go to some real number L. And we want to know that these numbers at infinity converge to that real number L. The question is, how do we do it? Did I answer your question?
So the statement of the goal is not necessarily doesn't necessarily have the submatrix thing, but like we're thinking about it that way.
Well, in order to construct the Y, where are we going to get rational numbers? We've got a matrix of rational numbers, and out of that, we're supposed to construct a sequence of rational numbers that has the property that.
But is the property I said true? Like, is that what we're getting towards? Like,
It's what we're getting towards. The question is how to do it, how to actually do it. Sean and then John.
Is the issue with just like the standard diagonalization, because you go all the way up to x of m, and then you go down to x of m, and then you gotta go from x of m back to q sub m, and that last part is the part that we can't necessarily bound, because we can, I guess, bound the first two, or we can pick like the first part to be like epsilon over 3. And
You're
then
getting there.
the second part, like,
You want to make this distance epsilon over 3 because this converges.
yeah,
You want to make this distance epsilon over 3 because that converges. You want to make this distance epsilon over 3 because that converges. And so the total distance will be epsilon over 3. I love it. But it doesn't work yet. Joe,
I think,
why not? I want to know why not. Why doesn't it work yet?
I think none of this works because if, like, okay. we can make each Cauchy sequence in every row converge to the same thing, even when we change all the diagonal values. Like, they can still be Cauchy, they can still converge to the same, still be in the same equivalence class.
You're getting there.
We can change them all to like 10 billion, get a Cauchy sequence, and it just doesn't help you with any.
Exactly right. Exactly right. So Joe is identifying one issue. One issue is, let's say you have this entire setup, right? If I change the nth row of the nth column to 10 billion arbitrarily, they're still all Cauchy sequences. You just have to get past, the the nth row in the nth column before it becomes Cauchy again, before it gets close. And then the limits are still Cauchy. So Yohasi had your hand up?
No, I think it's.
We're very close, Jeffrey.
So like for the idea where you're making like each leg, I guess, have epsilon over 3, can you just like straight up take the value of n that Cauchy gives you and like just force it to be that value in the row for each part of the thing, I guess?
That's almost the entire solution. What Jeffrey's identifying is, okay, maybe n isn't far enough. Maybe you can change the nth row to a billion, but eventually you got to be within epsilon of the limit in particular. So, but we just don't know how far out to go. But each row has a value where if you go out that far, you'll.
Not exactly that particular value, but like, I guess the sum of like all of this that came so far.
Okay,
Because that way you force it to like go horizontal.
yes. Okay, so let's make that precise. This is a complicated proof, which is why I can't tell if I'm going to be glad that we did this in lean or maybe not. But this is the kind of proof that having a theorem prover ground everything you're doing, I think will be really helpful. Let's find out. Here's the idea. So exactly right. The diagonal isn't far enough, but it's something like the diagonal. We have to go over far enough, but we have to make that choice. You see, before we go to prove either seq lim or is Cauchy with these epsilons and n's, we don't have an epsilon. We don't have an epsilon when we construct the sequence. So before we have a single epsilon, we have to say what the sequence is. So we need something that'll work regardless of how small epsilon is. And so what if for every row we make something, we make it get close to x0, but how close to x0 depends on the row in such a way that we get closer and closer to each x0. And then we use the fact that horizontally we always have a Cauchy sequence. So when you go far enough along, it might not be the diagonal, but it might be some farther distance into the matrix that you have to go before you're within epsilon over 3 of the limit. Does that make sense? So let me write that down. So idea, this is attempt 2. The idea is make each row within, we don't have an epsilon, but within something that goes to 0. Make the nth row within what? How about John?
1 over n.
1 over n. How about 1 over n within 1 over n of its limit, xn, by going far enough out, by going far enough, depending on n, into the sequence.
Why don't we have an epsilon?
Well, because the first thing we have to do, our goal is there exists a y such that we can prove that y is Cauchy, and we can prove that the limit of the xn's converges to the limit of the y. But the first thing we have to do is specify what the y is. We have to give the y before we can prove anything else. So we don't have you can't write a different y for every epsilon. That's G, right? So we have to give the Y without having any control on the epsilon. So the way we're going to do that is to just say, we'll be able to handle any epsilon by making a choice depending on n, making a choice of how close you want the sequence to get to its limit, depend on n. And how close doesn't matter, anything that goes to 0. Let's do 1 over n. 1 over n is a little annoying because you got a 1 over 0. 1 over n plus 1. Yeah, sure. So we're going to make the nth row within 1 over n plus 1 of xn. Okay, so let's think about how to do that. What was that called? HQ. HQ is the fact that for all n, this thing is Cauchy. So let's write that as a function. I'm gonna cook something up. So it's a function that sends n to HQ of n. HQ of n says is Cauchy, Q of n, that the nth row is Cauchy. Is Cauchy says for all epsilon there exists a capital N. What epsilon am I going to feed into this? 1 over n plus 1. Why is 1 over n plus 1 positive? By bound or something, whatever. Okay, so I know that every row, so what this says, what is the type of this right now? We already had our quiz, so this would be a good quiz question. Sean? Is that a hand?
It's a
Yeah.
function that maps a natural number and to like a statement of the type, like there exists a big N such that for all n greater than for all n. You
Yeah, this I can't use the same n. Let's make this I and j or something. For all I at least n, for all j at least I.
U N
Yeah, maybe j. Yeah.
U N or 1 over n plus 1 in this case.
Thank you very much. 1 over n plus 1. Okay. What this says is that you will get within 1 over n plus 1 of itself. But actually, I don't want to be within 1 over n plus 1 of myself. I want to be within 1 over n plus 1 of xn. Exactly. So it's not the Cauchiness that we want. So let me change this. So maybe this is going to be attempt 3. Attempt 3. Well, it's still attempt 2. Attempt 2, we were supposed to get within xn. How do we know that that sequence converges to xn? That was called seek lim of real of cow. Okay, so seek lim of real of cow says seek lim. Seek lim says for all epsilon there exists an n. So let's grab that. Let's grab seek lim of real of cow. So I'm going to construct instead a function that sends n to seek lim of real of Cauchy. What am I giving it as the Cauchy sequence? Exactly, HQN. And what is its limit? Sorry, what is it? What does this say? What does this now say? Can you keep it in your head? How many are completely and utterly lost? So, yeah. So remember what seek lim of real, what does seek lim say? It's that if a sequence is Cauchy, then it has a limit, and that limit is this real of thing. So this sequence is Cauchy, therefore it has a limit. And the limit is the real thing. So it says seek lim. Seek lim says for all epsilon positive, what epsilon should I feed into this? 1 over n. N plus 1, I guess. And then I'll feed in by bound. Okay, so what is the type of this? The type of this is a map that sends n to, there exists an n, so that for all I at least n, the difference between q n I and what I'll call xi, although xi is really seek real of, you know what xi is. It's that limited one, is less than, I guess strictly, 1 over n plus 1. Suhas?
I just xi and
xn, thank you. Okay, so given that for every n, there exists a capital N with this property, what do we want to do? Choose those n's. So choose, this is our fancy choose n h n using the function that maps n to seq-lim that whole thing. Do you want to see that in the written out? Let's take that one step in the game. Well, before we take that one step in the game, what are we going to do with this capital N? So capital N is now a function. And what it tells you is how far you have to go in the nth row before you're within 1 over n plus 1 of the limit. So it's not that we're going to take the diagonal. What are we going to take? Some much weirder thing. Some crazy thing. It doesn't. It might go backwards. I mean, there's no control horizontally from one to the other, how far out you have to go. But certainly you have to beat the fact that Joe could come along and change the diagonal entries to be a billion. You have to go some distance out. And that distance out is this capital N of little n. And so what will our sequence yi be? I'll take the ith row. I'll go to the ith row. How far out will I go? N of I, exactly right. N of I. So it's like the diagonal, but the diagonal is not good enough. The diagonal doesn't get us far enough along. And we made it so that this point, QI, is always within, if we're calling this xi, what's this distance? Exactly, 1 over, for some reason I'm calling these I plus 1. Which means we can beat epsilon over 3 if we go far enough down. We can beat epsilon over 3 this way. We can beat epsilon over 3 that way, and then we get our epsilon over 3 from the fact that these guys are Cauchy. Okay, does that make sense? That's going to be our sequence yi. So let's write that down. Hopefully you see it geometrically and not just algebraically. I want your intuition to be working just as hard as your formalism. So let y be the sequence from the naturals to the naturals, which is a function that takes a natural number and sends it to, I'm sorry, not to the naturals, to the rationals. It takes a natural number and sends it to Q n big N of n. Okay, so this big N, when we choose big N from the fact that for every n that there exists such an n, we'll get this big N as a function. And we can apply that big N, and that's our diagonal-like sequence that goes far enough out that it beats a bad situation, regardless of what that situation is. Okay, shall we plug that into the computer and just make sure it understands it? Okay, so let's write this out. So we want to say choose NHN using what? We're going to make a function that maps n to the fact that seq lim of real of Cauchy. I guess it got so long I said I'm not even writing the word seq. It's already too long. What Cauchy sequence? Or what sequence is Cauchy? HQN is the fact that that sequence is Cauchy. That says that we converge in the limit. Is this big enough, Roger, in the back? Yeah. So far, so good. What value of how close do I want to get to the limit? 1 over n plus 1. 1 divided by n plus 1. And why is that positive? By bound. Okay, ready to hit enter on this? It is, I mean, you accepted it, so it's, I just forgot to put it. It's not that I forgot. I don't know what to do. I want to, after this level, never see the name of this thing again. So I didn't add it, but I guess it's going to complain that I didn't add it as something that you're allowed to use, although obviously it knows what that theorem does since it did it. Okay, that's for me to work out. I'll make a little note. Think about how to, I guess I have to add it. I have no other choice but to add it to the game. That's what I'm going to investigate. Can I remove a theorem from later levels?
You could just.
Once I add it. What's that? That's what I don't know how to do. Maybe I can, maybe I can't. Okay, but obviously I have to give you access to that theorem in order to be able to solve this level. So I said it in natural language. I mean, I said it in the discussion that we're avoiding. But so what do we have? We have our sequence n, and we have the fact that this Hn for all I and j, as long as I is at least n of n, for all n, in the nth row, as long as you go up, as long as the ith column is at least n of n, then this god-awful thing, which is what? This is just q. This is nothing but this function that maps x to q of nx at n1 is just q of ni minus this limit. This is xi or xn rather. Xn is at most 1 over n. Okay, so we have what we want. We have what we want. We can clean this up a little bit. Should I give a name to these xn's so that we don't have to use them? Let's give a name to these. Let x be a function from what? Naturals to the reals, which sends n and maps it to, come on, maps it to real of Cauchy HQN. I think I can do that. And then I think I can change at HN. I want HN to look much nicer. HN should say for all n and I. Yes?
To clarify. Like those are real.
Yes. We're thinking of the x's as reals, but they're really not. I mean, they are. The x is a map from naturals to the reals.
Right.
And the way that we got the x is here. And maybe we can put a theorem about what the x's really are, but I don't want to do that right now. So let's just rewrite HN so that it looks nice. For all n and for all I, at least n of n, what do we get? We get that QNI minus XN is less than 1 over n plus 1. Does everybody buy that? Does Lean buy that? It does. Okay. So now it looks very nice. That's a much nicer view for HN. For every column, for every, you go down, for every row, for the nth row, if you go out at least n of n, q of ni minus the limiting value is at most 1 over n plus 1. Great. Now let's define our sequence. Let y be the sequence from n to q, which is the function that maps n to q of n and then big N of n. Boom. Use y. Our first thing is there exists a y. Use y. Okay. Now we need to construct a proof that y is Cauchy. So let's talk about why is y Cauchy? How come y is Cauchy? Okay. So you tell me. how come this sequence yn is Cauchy? So let's call this hy, and hy is Cauchy y by. Give me an epsilon, intro epsilon, epsilon h epsilon. Okay, I need to be able to go far enough out. What's the condition that I'm trying to, let me put it over here. I will want n and m large enough so that q of n minus q, or maybe these are the m's and these are the n's, are at most epsilon. How are we going to do that? Suhas.
Need 1 over n plus 1 less than epsilon over 3. You need 1 over n plus 1 less than epsilon over 3. And you need xm minus xm less than 3.
Exactly. So here's qn n of n, and here's qm n of m. And I don't know if this is in front or behind, but Suhas is saying we need to spend at most epsilon over 3 getting from qnn to xn. We need to spend at most epsilon over 3 getting from qnnm, whatever, I can't even say it, to xm. And we need to spend at most epsilon over 3 to get from xn to xm. And we need to know before we get going, we've only introed the epsilon, so now we have an epsilon. Question is, how far out do we have to go? What bound can I give for capital N so that for any n after that and for any m after that, we have that condition? So first of all, how do I get these two within epsilon over 3? Akil. What have we, how have we made these sequences so that we can get within epsilon over 3, no matter what epsilon is? Suhas?
You use arch prop to get like n plus
Arch prop. Arch prop guarantees that we go down far enough that this is at most 1 over n and this is at most 1 over m, and just make sure that both of those are less than epsilon over 3. Okay, so we'll need arch prop. So epsilon over 3, the reason it's less than epsilon over 3 is because 1 over n plus 1 and 1 over m plus 1 will be less than epsilon over 3. Okay, so after our intro, so this is, I'm going to try to go like this. So after our intro, we have arch prop, and we have to give it a proof that something is positive. What's positive? Epsilon over 3 is positive. Why is epsilon over 3 positive? Here's a problem. Arch prop takes a real number. Takes a proof that a real number is positive, and our epsilon is rational because we're dealing with rational sequences, right? The fact that the y is a Cauchy sequence, it's a Cauchy sequence in the rationals, and we have to show that it's Cauchy. Okay, so I have to do something like show 0 in the reals is at least epsilon over 3. And why is that true? Well, you want to just norm num or something? Norm num will normalize this away from the reals. It'll say, oh, wait, all of these things can be made rational. And in the rationals, I can prove it by bound. So I think norm num, and then bound will do that. Okay, so that says there exists an n. So let's choose n1, hn1, using all of this. Okay, so that's one upper bound. So that will ensure that both of these are within epsilon over 3 of their limits. And now y is xn within xm by epsilon over 3. Sean. Because it's Cauchy. Because it's Cauchy, that was called what? HX, I'm assuming. Let's look at what HX says. For all epsilon, there's an n, so that the guys are within any epsilon. So we take HX, we're going to specialize it to epsilon over 3. Probably, again, we have to send it up to the reals, because now this is going to be a statement about reals. So we have to send this up to epsilon over 3, and then we get an n, so that the xn and xm differ by epsilon over 3. Okay, does that make sense? So step 3 is choose N2 HN2 using, it was HX, and then I have to feed it the same nonsense about epsilon over 3. Okay, so that was the, that's how big, and so then how big an n should we take? The sum, yeah, n1 plus n2. Okay, we're trying to show that it's Cauchy, so now we need to intro little n. Yeah, little n, the hypothesis on little n that it's at least the sum of these two n's. Little m, the hypothesis that m is at least that, okay? So step 5 is intro n hn m hm. Are you keeping all of this in your head? Step 6. So what's the goal at this point? We haven't actually done anything to the goal. The goal is still that it's yn minus ym differ by epsilon. I'll just write this as yn minus ym differ by epsilon, but yn is secretly qn n of n, and ym is secretly qm n of m, or maybe the other way around. So then what do we want to do? Triangle equality, what are we going to add and subtract? And then, yeah, exactly. So step 6, I'll just skip to the punchline. Let's say we have F1, which is that yn minus ym is bounded by yn minus xn plus ym minus xm plus xn minus xm. And I trust you can fill in the details of that. Right? And then why is yn minus xn small? Because of arch prop. Yeah, that was n1 or something. So have F2, which is that yn minus xn is less than epsilon over 3. Again, I'm just going to sorry this out in the interest of I did want to get to new levels today, but whatever. Have F3 is that yn m minus xm. Let's do this. Now, let's not do it for real. Is less than epsilon over 3. These are bounded by 1 over n plus 1 and 1 over m plus 1, and n plus 1 and m plus 1 are both bounded by epsilon over 3. I'm not going to bother to chain that. We'll sorry that out as well. And how about xn minus xm? Have F4, which is that xn minus xm are bounded by epsilon over 3. That's by hn2, yeah, hn2 applied to n and by bound, and m and by bound. Okay, and then it's linearith, and then the last step is linearith. Linearith what? F1, F2, F3, F4. F1, F2, F3, F4. Okay, that will prove that y is indeed a Cauchy sequence. Let me, in the interest of time, let me just show you that is exactly what I did here. So in the game, so we did this choose n hn. And then we made it look a little nicer. We even made it look nicer than I did because let's make that change here. Let x colon equal the function that maps n to what? Real of cow seek HQN. And then this can be xn. That's a little bit nicer. Then we set y and we used y. And then here's a proof that y is Cauchy. Okay, so let's go into the proof of y is y Cauchy. Whoops. Y is y Cauchy. So give me the epsilon. It's exactly what we wrote out. Using arch prop. So here's arch prop. Epsilon over 3 is a lower bound, is bounded below by 0. That's n2. n1 is using hx, the fact that it's Cauchy. Then we use n1 plus n2. Then give me the n's and the m's. So there they are. Change the goal. Instead of yn and ym, change it to the q's. Specialize xn1 to that. Oh yeah, so I don't need these xn's and xm's. This already says xn minus xm is at most epsilon. These guys are bounded by, this difference is bounded by n plus 1. This is bounded by n plus 1. The xn and xm, I did all this work for you, so you didn't have to do it. We use ring. Anyway, this is maybe not so useful. Okay, so we get the fact that it's Cauchy. I'm just going to say in the game, in the interest of time, I'm going to say have hy is Cauchy y by sorry. Okay, will you allow that? Let's just say we've proved the fact that it's Cauchy, so that we can finish this god-awful proof and move on. So then use hy. It wants to know that does there exist a proof? I just said yes, it does. Use it. Now let's prove that this sequence does indeed have the limit. That the yn's, this yn sequence that we constructed, this red, funky, diagonal sequence that we constructed, actually has the limit. Well, we know that it's Cauchy, so it is equal to some real number L. Why do the xn's converge to L? Everybody see that? So that's what we have to prove. Next, the sequence of YNs is Cauchy, so it's equal to some L, some real number L, and why does the sequence of XNs converge to L? That's the next thing we have to show. Seek lim of these XNs converges to L. In fact, maybe it's nicer if I say, let L colon equal real of cow seek HY, and then show seek lim X. X is the sequence, L is the limit. Beautiful. So why do the XNs converge to L? Step 1. Intro. Yeah, let's take an epsilon. Intro epsilon H epsilon. Okay. Intro epsilon H epsilon. So we have this sequence of we have this sequence here of Q's that converge to L. Why do the X's, how do I get the X's close to L? Let me draw another copy of this so that we can mess with it. So here's the Q00, Q01, and QN0 and QN1, and so on. Here's X0 and XN, and that goes down to L, and then there's this funky sequence, whatever it is, the YI go to L. Okay, so Y is an XN. How come our goal after we put in a bunch of stuff will be to show that XN minus L is less than epsilon? Why? How are we going to get from an XN to an L?
We have a Q in that row that's close to L.
Yes.
So we can bound to that, and then like that's epsilon over 2. And then the Q sub n is also epsilon over 2 away from L.
Excellent. You guys are getting the hang of this. This thing is actually a row, right? The yi's are a row converging to L. We know seek lim, what is that called? Seek lim of real of cow or something? Of cow, some horrible thing like this. And the fact that the y's are Cauchy says that the y's converge to L. So give me feed in epsilon over 2, the fact that epsilon over 2 is large enough, and choose an N1, HN1 using this. So that gets us a distance of epsilon over 2 between Q and N and L. And how do I get the distance and epsilon over 2 from Q and N to XN? Other than Sean? We did it once already. Why was it true? Other than Suhas, because he gave us the right answer last time. Akil. Archprop. This is bounded by 1 over n plus 1. So choose N1, N2, HN2 using archprop. And then follow the rest of the argument. Okay. Then I'll just write it in natural language. Then absolute value of xn minus L is bounded by, so of course, use N1 plus N2 and intro NHN. And now xn minus L is bounded by xn minus, I can just say yn plus yn minus L. This thing is less than 1 over n plus 1 by construction, which is less than epsilon over 2 because of archprop. This thing, yn minus L, yn converges to L. So because of this seek lim of real of cow, this is less than epsilon over 2 because we made n large enough. Okay, so I'm curious. Would you have preferred this argument in natural language, or are you glad that we didn't even fully, just the threat of having to do it formally made us write down an argument that I think is more precise than the kinds of arguments you see in natural language. Does it make sense? Does it make perhaps better sense than it would have otherwise? Daniel.
So I have a question.
Yeah.
In the proof you wrote for
The Cauchy?
like HY Cauchy, you used you used convo Cauchy. I'm just wondering, how do we know, how do you know that every real Cauchy sequence converges if not by this exact process?
We don't know that we're proving that real Cauchy sequences converge. The reason rational Cauchy sequences converge is because that's what the reals are.
Right, but I thought wait, no, why would you use that real Cauchy sequence converge with Y?
Right, so I
thought it was referring to real.
Yeah, the y's are rational. The question is, how do we get out of this big matrix of rational values, how do we get some subsequence that will be Cauchy and hence converge to a real number, so that this Cauchy sequence of xi's converges to that limit? Okay, so the upshot is, this argument has nothing to do with rational numbers or real numbers. It is purely a statement about completions of metric spaces. So anytime you have a space and you have a norm on it and you complete it by taking equivalence classes of Cauchy sequences, automatically that space is now complete by this kind of quasi-diagonalization. It's a what is it? A shaky hand diagonalization argument. It's not the diagonal. It looks like it should be the diagonal. The diagonal is no good. That's the moral of today's lesson. The diagonal works in 1,000 places. Cantor made a living out of this argument, and it doesn't work here. It almost works. It needs a little push. That's the moral. All right, we're out of time, so lecture 15 has been broken up into 2 lectures. We'll pick up with lecture 16 next time.